Hey, what's going on, guys? This video that I'm making is on the intermediate value theorem. So in calculus, there's that section on continuity. We covered some of it in class today. We didn't get to cover everything. And so one big part of that section is the intermediate value theorem. So we really need to get that theorem down. So let's get started. In calculus, there's a few big theorems, something like 4 or 5 really big theorems, and the intermediate value theorem is the first of the big theorems. So again, we really need to get this down. So let's see what the intermediate value theorem is talking about. All right, so let's see what this theorem says. It says, suppose f is continuous on the closed interval ab, and let n be any number between f of a and f of b, where f of a is not equal to f of b. Then there exists a number c in the open interval ab such that f of c equals n. Got it? Okay, it's complicated the first time you read it, but you read it a few times and we'll break it down here and then it'll make more sense, I hope. So I'm going to break this down into a lot of little pieces here. First of all, closed interval. What does that mean? You know what an interval is, but if you have brackets on the left and the right, we call that a closed interval. Whereas over here, down here, we have an interval, and when you have parentheses on the left and right, that's called an open interval. Okay, so closed interval here, open interval here. So that's the first thing. Okay, next, what does it mean when it says that f is continuous on a closed interval? Well, we talked about that in class already. It means between a and b, f is fully continuous. So at any number inside the interval, it's fully continuous. But at the number a and at the number b, it's not fully continuous. What's happening at a? It's continuous, but only on one side. It's only continuous from the right at a. From the right at a, because you kind of go for it like that to get to a. Continuous from the left at b, like that. So one more time, what does it mean to be continuous on a closed interval AB? It's got messy. It means that f is fully continuous. Let me go and write that down. So f is fully continuous at any number that's between a and b. Okay, so if you pick any number between a and b, it's fully continuous. By the way, let's go over that. What does that mean to be fully continuous at a number? It means if you want to take the limit as x goes to that number of the function, you can plug it in. So for example, let's say that number, if r is between a and b, so not a, not b, but between there, then if you do the limit as x goes to r of the function, you can find the answer by plugging in. The answer would be f of r. That's the limit way of thinking of continuous, fully continuous. There was also a graph way. A graph way, if it's fully continuous at r, would look something like this. Let me put the number r down here. It means that you draw the graph through r. In other words, you could start a little before r, end a little bit after r, and the entire time draw the graph without taking your pen off the paper. Then it's fully continuous at r. So at every number in this interval, AB, between a and b, the function is fully continuous. Okay, the next thing is, what does it mean if the function is, what does the bracket on the a mean? It doesn't mean it's fully continuous. It means it's continuous from the right at a. So because there's a bracket, sorry, it's taking a long time to erase here. Because there's a bracket right here on the a, that means it's continuous from the right at a. So f is continuous from the right at a. I know it gets confusing because a is written on the left, but because that bracket's on the left there, it's continuous from the right. What does continuous from the right mean? Well, here's what it means. It means if you want to take the limit as x goes to a of the function, I don't know what the answer is, but if you take a right-hand limit, then you can plug in to get the answer. So that's what it means to be continuous from the right. That's a limit definition of what it means to be continuous from the right. From a graph definition, what does it mean to be continuous from the right at a? So let's put a over here. It means you can draw the graph starting on the right of a, and you can get to a. You can't get past a, but you can get to a. without taking your pen off the paper. So it usually looks kind of like an endpoint. It doesn't have to look like an endpoint, but you start a little bit to the right of A and you can draw the graph all the way until you get to A. I don't know about past A, but all the way until you get to A without taking your pen off the paper. That's what it means to be continuous from the right at A. Okay, what does the bracket on the B mean? It's continuous from the left at B. So it's not fully continuous at B, but it's continuous from the left at B. Okay, let's go ahead and write that down. Okay, so it means F is continuous from the left at B. From a limit perspective, this means that if you take the limit as x goes to b, well, if I'm taking a full limit, I don't know what it is. But if I say continuous from the left, it means if you're taking a left-hand limit as x goes to b from the left, you can get the answer by plugging in. And if you want to think about the answer from a graph, what does continuous from left mean at b from a graph? It means you can draw the graph starting to the left of A, and you can get to B, starting from the left of B, and you can get to B. You may not be able to go past B, but you can get all the way up to B, including B, without taking your pen off the paper. Okay, so one more time. Let's talk about what it means to be continuous, for F to be continuous on a closed interval. I'm going to basically say that that means the function is nice. It means you can draw it from A to B. You can start at A, you can end at B. Think of it as having two endpoints. So there's a point at A, there's a point at B, and you can draw the graph from A to B the whole time without taking your pen off the paper. It also means that it's fully continuous at any number between A and B. It's continuous from the right at A, and it's continuous from the left at B. So we'll go ahead and draw an example here of what such a graph would look like if I draw the whole graph. So I want you to imagine graphs that start at A and end at B. So it has endpoints. And it's going to be fully continuous between A and B, continuous from the right at A, continuous from the left at B. It basically means you can draw the graph the entire time without taking your pen off the paper. No holes, no asymptotes, nothing. So here's an example. So the graph starts at A, ends at B. So, let's say this is the point on the, well, let's make it red. This is the point on the graph when x equals A. Let's say this is the point on the graph where x equals B. It could be higher or lower. Let me just put it like that for now. That means you can start the graph here, end the graph here. You can draw the graph, start at the first dot, end at the second dot, and the whole time draw it without taking your pen off the paper. So it could look something like this. This is one example. Any kind of graph, any way you can connect those two dots without ever taking your pen off the paper, in that situation, F is going to be continuous on the closed interval AB. Closed interval because it's fully continuous in between, and because the graph heads towards the dot that we get on both ends, it's continuous from the left at A, from the right at A and from the left at B. That's what continuous on a closed interval means. So that's the first thing it says. So I want to think about the structure of this theorem. It says if you have a nice function, okay, so if you have a function that's continuous on a closed interval AB, a nice function, and one other property, you have some property here. If you look over here, the second sentence, this sentence has to do with outputs. It says, see, f of A is an output, right? You plug in A to the function, you get f of A, that's an output. This is another output. And n is a number between. So think of all these numbers as on the y-axis, or think of them as outputs. So if you have a number between these two outputs, that's what the second sentence says. Then we get the conclusion of the theorem, bottom. Oops. So the third sentence is the conclusion, and the conclusion has to do with inputs. Then there's a number C between A and B. Look, that says A and B. We're talking about inputs. There's a number C somewhere in between there that does something. Okay, so I want you to think of the structure of the theorem like that. So let me go over it real quick. So here's the structure. If, two things. First of all, f is a nice function. Means continuous on a closed interval AB. Okay, and the second thing, something is happening with the outputs. We'll talk about it more later. So if you have a nice function and some certain thing is happening with the outputs, then we get the conclusion. There's an input that does something. Okay, so let's go over. So that's the structure. When you're trying to memorize this theorem, because it's very likely they'll ask you to state the theorem on a quiz, on exams, and so forth. We want to first remember the structure. If these two things happen, then this third thing happens. Okay, so if you have a nice function, don't say nice though, just say continuous on a closed interval AB. And something happens with the endpoints, which we're going to discuss in more detail right now. I'm sorry, something happens with the outputs. So something happens with the outputs that we'll talk about. Then there's an input of the function that does something. It does this, whatever that means. All right, let me finally go ahead and do some examples to understand what's happening with these outputs, what's happening with these inputs. This is not the kind of question I would ever ask you on a quiz or anything. This is just so we get comfortable with the intermediate value theorem. So that's why I wrote getting comfortable with the intermediate value theorem here. Okay, so it says suppose f is continuous on a closed interval, and I gave you a closed interval, I gave you 2 to 6. I'm also telling you what happens if you plug in the endpoints to the function. So if you plug in 2 to the function, you get 10. If you plug in 6 to the function, you get 18. Then what can we say? So here's what I'm going to do. I'm going to draw things a little bit non-standard. Okay, this is the x-axis here. Normally we draw the y-axis like this. This time I'm going to not do it that way. I'm going to put the y-axis up here. So I want you to think of inputs down here and outputs up here. Okay, f is continuous on 2, 6. 2, 6 stands for inputs. So I'm going to put a 2 and a 6 on the x-axis for inputs. Okay, and over here I'm going to draw my function as a box. Remember, function is a machine. So I'm going to draw it as a box. Okay. Now what the information is telling me, so if I say f is continuous on a closed interval, it means it's a nice function. So this function here is nice. It means you can draw it the whole time from 2 to 6 without taking your pen off the paper. I'm not going to draw the function here. I just want to think of inputs and outputs here. So if you plug the number 2 into the function, you get out the number 10. If you plug the number 6 into the function, you get the number 18. Okay, so that's the information we have. I know what happens when you plug in 2, you get 10 out. When you plug in 6, you get 18 out. What the intermediate value theorem says is since you can get 10 out of the function and you can get the number 18 out of the function, then you can get any number between out of the function. For example, make up a number between the outputs. So think of it as a game, okay? Let's do it this way. I'm going to give you an output of the function. Then you're going to find an input that gives me that output. Okay, so that was a real important sentence I said, but let's practice it here. So I'm going to make up an output between 10 and 18. So let's say, 16. I just made up some random some random output, but between 18 and 10, okay? And this output, by the way, is going to be called n in the theorem. So that n has to be between 10 and 18. The theorem says there's a number down here. Now I don't know what it is, but there's some number down here. We're going to call it c. That if you plug it into the function, you get 16. Now, here's what I'm basically trying to say. You can get, for sure, 10 can come out as an output of the function. 10 can come out of this function. 18 can come out of the function. So any other number you pick between 10 and 18 can come out of the function. That's what it's saying. And what do I mean when I say it could come out? I mean, there's got to be some input you can plug in to get that number out. And that input, incidentally, has to be between the 2 and 6, the interval that we started with. Let me give you another one here. So let me change the number here. Let's say instead of using 16, oh, I kind of lost my y-axis there. Okay, let me draw another y-axis. That's a pretty horrible one. Let's draw another one. Okay, so one more time. We started with the function continuous on the closed interval 2, 6. And I'm telling you what happens if you plug in the endpoints of your interval. So if you plug in 2, you get 10. If you plug in 6, you get 18. So 2 in gives you 10 out. 6 in gives you 18 out. So now what I know is if you pick any other number between 10 and 18, anything, let's try 12.5. So if I start you out with with an output, so if I start you out with a number between the outputs of the endpoints, between 10 and 18, the intermediate value theorem says then that there's some number between 2 and 6. I don't know where it is, somewhere in here. Let's go ahead and just say that it's, I don't know, let's say it's here. I don't know what the number is. I just know there's one between 2 and 6. We're going to call that number C. So if you plug C into the function, you get 12.5 out. So if 10 can come out of the function and 18 can come out of the function, then any number between 10 and 18 can come out of the function. That's what a continuous function is. So think of it as like a game. If I give you an output that I want the function to have, you could find the input that gives me that output. The output that I'm going to come up with, I'm going to call it n. N has to be between 10 and 18. And the number, the input that exists by the intermediate value theorem, that's called C. That's got to be between 2 and 6. Let's do one more example just like this one. Okay, f is continuous on the closed interval -4 to 3, and f of -4 is 30, and f of 3 is -5. So what can you say about that? Okay, I'm going to go ahead and draw an x-axis again and a y-axis again. So think of these as the inputs, and think of these as the outputs. Okay, so -4 to 3, those are inputs. I'm going to put those down here, -4 and 3. And I'm going to draw the function machine, so we'll draw it like this. Okay, so the problem says that if you plug -4 into the function, you get 30. Okay, so let's say we get that number here. If you plug in the number 3 to the function, you get -5. Now, it doesn't matter that when you plugged in the bigger number, you got the smaller output this time. In the last problem, when you plugged in the bigger number, you got the bigger output. It doesn't really matter. All I really care about is that the two outputs are different. Whether the second one is bigger than the smaller one or smaller than the, whether the second output's bigger than the first one or smaller than the first one, doesn't matter. So now here's what the intermediate value theorem says. It says if you pick any number between -5 and 30, you can get that function out of the machine as well. So we know -5 can come out of the machine. How? By plugging in 3. We know 30 can come out of the machine. How? By plugging in -4. Once I know that, and the fact that I know that f is continuous, then I know that if you pick any number you want, any other number between -5 and 30, then that can also come out of the machine. So for example, let me go ahead and pick a number, any number between -5 and 30. Let's say I pick, I don't know, let's say I pick the number 4. And that's going to, in general, be called n, the number that you pick. So n is 4. 4 is definitely between -5 and 30. So since -5 can come out of the machine and 30 can come out of the machine, 4 can come out of the machine. You're going to say, okay, how can you get 4 out of the machine? Well, I don't know what the input is, but the intermediate value theorem says there's some number between -4 and 3 that if you plug it in, you'll get 4. That number is called C. So I'll just label it here as C. I don't know what number it is, but if you plug that into the function, you get 4. That's what the intermediate value theorem says. This is true for any number between -5 and 30. So let me say it one more time. -5 can come out of the function by plugging in 3. 30 can come out of the function by plugging in -4. And f is a nice function, it's continuous. So you can get any other number out of the function. Any other number between -5 and 30 you can get out of the function by plugging in some input between -4 and 3, even though I don't know what it is. So let me go ahead and show you one other, let me pick one more number here. So one more time, any number you want, in particular 0, and 0 is probably something we're going to use often, but do you guys agree that 0 is between -5 and 30? Okay, so since -5 and 30 are both outputs of this function and it's continuous, then 0 must be an output. You're going to say, okay, well, if 0 is an output, there must be something you can plug in to get 0. You're right. Do I know the number? No. But the intermediate value theorem says there's some number between there and there. We're going to call it C. that if you plug that into the function, you get 0. So that's what the intermediate value theorem says. Okay, can you get a number bigger than 30 or less than -5? Maybe, depends on the function. But if it's continuous on a closed interval, if you plug in the endpoints, in this case we get -5 and 30, then you can get any other number you want between -5 and 30, guaranteed by the intermediate value theorem. The number you plug in to get that output is called C. The output you want to get, that's called N. So in this example, N is 0. Okay, so N has to do with so N is a number between the outputs. C is a number between the inputs. Okay? If you specify an N that's between f of A and f of B, f of the two endpoints of the interval, then there must be an input that will give you that output. Let me go ahead and draw this picture in general without any numbers in it. So I'm going to draw the same kind of picture here, but I'll just put A and B because I want to really understand this theorem here. So here is an x-axis, here is a y-axis, and I'm going to put the numbers A and B here. A and B are inputs. When you see f of A, f of B, those are outputs. So, okay, so we have A and B, and this is the function machine again. And then it's saying if you plug in A, well, if you plug in A to the function, the output's going to be f of A. That's how you write the output. A is the input, f of A is the output. If you plug in B, the output is f of B. Now, I know I'm drawing these arrows straight. Don't really worry about that, okay? What I'm drawing here is that I'm drawing a situation where f of B is bigger than f of A, but if f of B is less than f of A, whatever, it doesn't matter. All I care about is that they're different, so that there are numbers in between. That's all I care about. Okay, so if f is continuous on a closed interval AB, okay, and then you pick a number n between f of A and f of B. So n is a number that you're thinking of as an output. So if you pick any number at all, let me go ahead and put a number in between f of A and f of B. So like, let's say there, any number between f of A and f of B. Then the intermediate value theorem says that there's a number C between A and B. So if you plug it into the function, you get n. That's what the intermediate value theorem says. Okay, so let's practice stating it once. Remember the structure. It was, if f is nice, and some story is happening with outputs, then there's an input that does something. Okay, let me see if I can, well, I can't squeeze it in here, but let me say it first. Okay, so the first thing you would say if I say state the intermediate value theorem, you would say if f is continuous on a closed interval AB, okay, that means the function's nice. It's continuous on the closed interval AB with brackets. Okay. The second thing you would say is, and if you have a number n between f of A and f of B. So if you picked a number between f of A and f of B. So basically what I'm saying is you plug in A to the function, you get f of A as an output. You plug in B to the function, you get f of B as an output. And then you have a number n that's between your two outputs. So if n is between f of A and f of B. You don't have to mention that f of A is different than f of B, but they need to be different. Otherwise, there isn't going to be a number n between f of A and f of B. Then you're going to say the conclusion of the intermediate value theorem. Then there's a number C. Where is that number C? Between A and B. So you say, then there's a number C between A and B, such that if you plug it into the function, you get n. And to say plug it into the function, you get n is basically saying f of C is n. If you plug C into the function, you get n. Okay, let's go over it one more time. Let me go ahead and try to do it without the picture. So let's erase the picture, and then let's go ahead and write it. I know you can go back to the other slide and look at it, but try to keep the picture in your mind as you're saying it, and then please practice it a lot. Practice saying it, go over this over and over again so you can really understand the ideas here. Okay, so the first thing you're going to say, if I say state the intermediate value theorem, you're going to say if f is continuous on the closed interval AB, and something else happens. Be careful, sometimes I have students write then right now. So you want to say if two things happen, then a third thing happens. So that's one thing. So if this and if this second thing happens, what's supposed to happen? Think about outputs right now. We have f of A and f of B are the two outputs of the endpoints. and you need a number between them. So you can say, and n is a number between the outputs f of a and f of b, comma. Then, now we'll write the conclusion. The conclusion is there's a number, we're thinking about the input, so then there is a number. What's the number called? The number is called c. Between where and where? Between a and b. So you can write between a and b. You could also write in a comma b, which is the same thing as saying between a and b. Such that what happens? If you plug in c to the function, you get n. Again, make sure you get those things straight. Sometimes I see students write f of n. That doesn't make sense. N is an output, c is an input. So you put c into the function, you'd get f of c, and that's supposed to equal n, such that f of c equals n. All right, let's go over it one more time. If f is a nice function, continuous on a closed interval, if you plug in a and b, because those are inputs, if you plug a and b into the function, you get f of a and f of b. If you pick a number that's between those outputs, then n is also an output. How? By a number c. There's a number c that you can plug into the function. That number c is between a and b, such that if you plug it into the function, you get n. That's the story there. All right, guys, so I'm hoping that makes sense from a plugging in function standpoint. Now I want to go and show you a picture, a graph of the situation. In this situation here, I have the x and y axis the way they're supposed to be now. Okay, so for the intermediate value theorem, we have a function that's continuous on a closed interval a, b. So again, the graph will start at a, starts at this point here. Notice I'm putting the y coordinate as f of a. So it starts, that's the start of the graph. Okay, it starts at the point a, f of a. It ends at the point b, f of b. Now I happen to put the second dot higher than the first dot. If the second dot was lower than the first dot, that's fine too, but I have to draw something. So I'm drawing it like that. Okay, so those are the endpoints of the graph. So A is an endpoint, B is an endpoint. If you plug in A, the output is f of a. If you plug in B, the output is f of b. And I have a function continuous on the closed interval AB. What that means is you can connect these dots with some kind of graph without taking your pen off the paper. I won't draw the graph yet. So again, if you were stating it, you say, if f is continuous on a closed interval AB, which means, again, nice graph connecting these dots. Then, oh, and not then, sorry, and you have a number between these outputs. So I need a number between here and here. What's that number called? It's called n. So there we go, n. So you have a number n between the outputs. Okay, what I'm going to do now is I'm going to draw a horizontal line where the n is. So a different way of saying it is, if you draw a graph that connects these two dots, then it must cross this line where n is somewhere. Let me go and draw a graph, just one example of a graph that connects the dots that's continuous. So like that. Again, that could be drawn without taking your pen off the paper. Do you see where it crosses? In this example, it crosses 3 separate spots. Right? It crosses here, and here, and here. Those 3 spots where it crosses, here, let me just go to the next slide here. Those are the 3 spots where it crosses, those green dots there. On those 3 spots, if you look at the inputs, the x coordinates of those points, they're going to be called C. We have 3 different C's here, so I'm going to call them C1 and C2 and C3 like that. Okay? The intermediate value theorem guarantees that there's going to be a number that if you plug it into the function, you get n. In this picture, there's more than one. There's 3 different numbers that give you n. So we have f of C1 is n, f of C2 is also n, f of C3 is also n. So it totally depends on the function. I don't know. All I know is that if you have a continuous function, it's going to cross the line at least once. In other words, there's going to be at least one input that if you plug it into the function, you get this n as an output. In this case, I know we have 3, but at least one. Okay. So the thing I want to mention now is there's going to be times where I'm going to want 0 as an output. Okay. If I want 0 as an output, then I need one of these to be negative and one of these to be positive. I would want my n to be 0. So if my n is equal to 0, then I need one of these to be negative, one of these to be positive. I know it's not drawn like that here, but in examples, sometimes you want the output to be 0. So that means f of a and f of b need to be 0. Okay, hopefully that made some sense. Let's go ahead and look at a couple of examples of applying the intermediate value theorem now. Okay, this example says, show that there's a root to the equation 4x cubed minus 6x squared plus 3x minus 2 equals 0 between 1 and 2. Okay, I first off want to mention that this problem is actually worded really incorrectly, but this is the way they write in the book, and so I guess this is the way I'll put it on a quiz. But let me just make sure so we're saying things correctly. If I give you an equation, this is an equation because you see an equal sign here, then I will say the correct way of saying things is show that there's a solution to this equation. They shouldn't have said show there's a root of the equation. They should have said show there's a solution to this equation between 1 and 2. Okay, second thing, what does root mean? Root is a word that doesn't have to do with equations, has to do with functions. So if I give you a function, let's say I give you a function, let's say you plug in 2 and you get 0, then 2 is called a root of the function. If you have any function, if there's a number you can plug in and you get 0 out, then the input is called a root. So if you want a quick example of roots, if I look at something like f of x equals x squared minus 5x plus 6. Let me go ahead and plug in some numbers here. If I plug in 0, let's plug in 1, let's plug in 2, let's plug in 3, and let's plug in 4, just to see what we get out. If you plug in 0, you get 6. If you plug in 1, you get 2. If you plug in 2, you get, let's see, 4 minus 10 plus 6, you get 0. If you plug in 3, you get 9 minus, you get 0. Plug in 4, you get 16 minus 20, negative 4, you get 2. Okay, because we got 0 out here, 2 is a root. Because we got 0 out here, 3 is a root. 0, 1, and 2 are not, 0, 1, and 4 are not roots because these are not 0 here. This one, and this one are not 0. Okay, so in this example, the roots are 2 and 3 in this quick example that I did over here. That's what a root is. So one more time, let's make sure we understand the words. A root is something you use when I give you a function. A root is an input whose output is 0. So if you can think of any number that you can plug into the function and get 0 out, then your input is a root. Okay, and then again, when I ask you, when I give you an equation, a root of an equation doesn't make sense. It should say a solution to the equation. They're kind of related, but they're not exactly the same thing. Okay, so now what this problem is saying, let's make sure we understand the question now. It's saying show this equation has a solution between 1 and 2. I want you to understand something. When we're done with this problem, you may feel a little unsatisfied because normally when I give an equation, I ask you to solve the equation, give me the answer. That is not what we're doing here. I'm not going to find the answer. I'm not going to find the solution to this equation. I've actually given you an equation that's very hard, if maybe even impossible, without a computer to figure out what the solution is. I don't want to know the solution. It does not say solve the equation. It does not say find the solution. It doesn't say find. It just says shows there is one. Okay, so why would I want to do that? Let me give you a quick example. Imagine this equation here is super important for a physicist to solve. But a physicist can't figure out how to solve it, so he programs a computer to solve it, and it's trying to solve it, and it can't come up with a solution. Well, after months of trying, the physicist can go to the mathematician and say, hey, does this equation even have a solution? Because sometimes equations don't have solutions. So the mathematician can use the intermediate value theorem and say, okay, I've used the intermediate value theorem and I've concluded it has a solution between 1 and 2. So at least you tell the physicist, hey, you're not wasting your time. It has a solution. It's between 1 and 2. Keep looking. Okay, so again, I know it's a weird result. We're not actually going to find the solution, but we're just going to see that it has one, but I'm not going to know what it is at the end. So it's like, does it have one versus does it not have one? That's kind of the idea. Okay, so what you're going to do is we need a function if we're going to use the intermediate value theorem. So we're going to start off. So here's what we're going to do. I need a function in order to use the intermediate value theorem. So we're going to call whatever's on the left of this equation here, we're going to call that f of x. Now I do want to warn you in other problems, if there's something other than just the number here, if it's not just 0 or like a 3 or something, if there's x's over here, what you want to do is you want to move them all over. We're going to need only a number here. Most of the time we want 0 here, but you could actually put any number you want there. It could be any number, but anything that has an x in it, you need to move over to the left side. Okay, so instead of trying to show this equation has a solution, I'm going to start off by saying let f of x equal this function that's on the left here. And I'm going to show you that this function has a root. What do I mean? I'm going to show you that there's a number you can plug into this function and get 0. If there's a number you can plug in to get 0 out of this function, that number will be a solution to this equation. Okay, so that's the idea. So how am I going to show you that it has a root? Okay, I want to show you there's a number you can plug in to get 0. So I have to start off, I need an interval. Okay, well, they tell us the interval in this problem. Now listen, some examples they don't give you an interval, then you're going to have to make it up. But in this example, they give you the interval. What if they don't give you the interval? Well, it's like this. What output do I want? I want 0 as an output. That would mean there's a solution to this equation. I want 0 out. So if I want 0 out, I need an interval where if you plug in one endpoint, you get a positive number, and when you plug in the other endpoint, you get a negative number. That way 0 is between the outputs. So you can make up any interval you want as long as 0 is between the outputs. Okay, but they give us the interval here, so that's good. So now I'm going to write down that f, I'm basically writing down what the intermediate value theorem says. It says if two things, then a third thing, right? So I'm going to tell you, hey, the first two things are true, therefore the last thing must be true. What was the first thing? That f is continuous on the closed interval. So I'm going to write down first, f is continuous on the closed interval 1, 2. Okay, that's the first thing. Now, why is that the case? We need to say why that's the case. So I'm going to expect you to write why, and here's what you're going to say. This is because f is a polynomial, and so continuous everywhere, because we know polynomials are continuous everywhere. So that means it's continuous on negative infinity to infinity. So since this is less numbers than negative infinity to infinity, so f is continuous on the interval we want, 1 to 2. So you have to make some kind of argument like that. Okay, so we've done the first thing. F is continuous on a closed interval 1 to 2. The second thing I want is, well, okay, tell me what the number n is. Remember, what's the output I want? I want 0 as an output, so n is 0. So now I need to say that n is between f of a and f of b, but I'm not going to write n, I'm going to write 0 instead. So the second thing is 0, remember that's n, is between, and instead of writing f of a and f of b, I'm going to write f of 1 and f of 2. In other words, if you plug in the two endpoints to the function, 0 is between those. Okay, if you don't believe me, let's write down why. Because if you do f of 1, let's plug in 1 to the function. What do you get? Plug in 1 here. Looks like it's 4 minus 6, that's negative 2, plus 3 minus 2, it's negative 1. Okay, so it's a negative. And if you plug in 2 to the function, oh boy, what is that? I don't have any room here, so I'm not going to write it down. But it's 4 times 2 cubed, that's 32. Minus 6 times 2 squared, that's 24. So 32 minus 24, that's 8. Then it's 8 plus 3 times 2, that's 6. So that's 14. Minus 2, it's 12. Okay, and all I care about is this is less than 0. This is greater than 0. So when you plug in 1, you get a negative. When you plug in 2, you get a positive. So 0 is definitely between them. So we've shown that thing. Okay, we're almost done, but I am out of room. So hopefully you can pause the video, write this down, and leave some more room so you can write down the rest of what you need to write. So one more time. F is continuous on a closed interval 1, 2. We said because it's a polynomial and it's continuous everywhere, it's definitely continuous on 1, 2. Then the second thing you need to use the intermediate value theorem is you need a number n between f of a and f of b. When you're trying to get a root of a function, we need n to be 0. So you're going to say 0 is between f of a and f of b, in this case f of 1 and f of 2, and you can just check it by plugging in and go, hey, look, one's negative, one's positive. And you see now that if they don't give you an interval, you need to come up with some inputs, 2 different inputs, like 1 and 2, so that when you plug in one of them, you get a negative. When you plug in the other one, you get a positive, so that 0 is between them. Okay, so those are the 2 things you need in order to use the intermediate value theorem. So now I can use the conclusion of the intermediate value theorem. Let me go ahead and erase some stuff here. Okay, so since we just showed that the 2 things you need in order to use the conclusion of the intermediate value theorem, let me say that again. Since we just showed that the 2 conditions of the intermediate value theorem are satisfied, we can use the conclusion of the intermediate value theorem. What was the conclusion? Well, here's what you're going to write down. First, you need to write down, so by the intermediate value theorem, write it like this. So by the intermediate value theorem, like that. What was the conclusion? The conclusion is there's an input. What is it called? It's called C. There is a number C. Where is that number? It was between A and B. Some students accidentally get that confused with f of a and f of b. It's between A and B. You have to keep straight what are inputs, what are outputs. So there's a number C between which numbers? Between 1 and 2, such that what? That does something, right? There's a number between 1 and 2 that does something, such that if you plug this number C into the function, you get n. I'm not going to write n. What was n? It was 0. There's a number you can plug into the function to get 0. So you see, we just concluded by the intermediate value theorem that there's a number you can plug into the function to get 0. Notice I didn't find the number. I just know by the intermediate value theorem there is such a number. I also know it's between 1 and 2. And because f of c equals 0, that means c is a root. So c is a root of the function f, which means c is a solution to the equation. Yeah, that's the end of that story there. Again, you might feel a little weird because we didn't find the solution, but that's the way it is. I didn't say find the solution. I just said show it has a solution. Let me just summarize real quick. What did we do? We first we wanted to see if we can use the intermediate value theorem. So in order to use it, we need a function continuous on a closed interval, and this function is continuous on the closed interval 1 to 2. We also need a number between f of 1 and f of 2, and when you're trying to find a root, that means you're trying to get an output of 0. That means n is 0. Whatever output you're trying to get, that's what n is. So we wrote down that 0 is between f of 1 and f of 2, which it was, because we plugged them in. If we plugged in 1, we got a negative. When we plugged in 2, we got a positive. So we can use the conclusion of the intermediate value theorem. What's the conclusion? That there's a number between 1 and 2 that if you plug it into the function, you get 0. And that means c is a root, which is equivalent to saying that we have a solution to the equation. Yeah, that's how that one goes. Okay, we have one more similar to this. Okay, show that the equation x sine x plus 3x equals 7 has a solution. Okay, this one's written better, okay, because it is an equation, so that's what we want to show. We want to show it has a solution, not a root or anything like that. All right, so if we're going to use the intermediate value theorem to do this, the first thing I need to come up with what function I'm going to use. So there's 2 different ways you can do this. One way is you can call this the function, and then you want to show that it has an output of 7 somehow. Or a second way to do it is you can minus the 7, put the 7 over here, you would get a 0 over here, and then show that that function has an output of 0, in which case we would call that a root, show that function has a root. So let me see, which way do I want to do this? I'll tell you what, I'm going to do it the first way. I'm going to leave the 7 on the right side, and I'm going to do it that way. And then why don't you try it afterwards where you move the 7 over and you want to get an output of 0? Okay, so let me go ahead and write down what my function is. So we're going to say let f of x equal x sine x plus 3x. Okay, so if you do it the other way where you move the 7 over, your function would be this minus 7, and you want to show that you can get 0 as an output, or 0, or it has a root. 0 can be an output, the same thing as saying it has a root. But if I get rid of the 7, so I just leave the 7 on the right side, I want to show that this function has an output of 7. There's something you can plug into it to get 7 out. That's what I want to show. Okay, so the next thing now is to come up with an interval. Because I want to get 7 out, think about it like this. I'm going to draw this x and y axis like I had before. You have to come up with the a and the b. Okay, so this is like the inputs, this is like the output. But I want 7 out. 7 is going to be my n. So you got to come up with a number that you can plug in to get something less than 7, a number you can plug in to get something bigger than 7, so that 7 is in there. Of course, this doesn't have to be on this side. This could be on this side, and this one could be on this side. It doesn't matter. All I know is I want that, so either f of a is here and f of b is here, or reversed, f of b is here, f of a is here. So I don't know. I just need 7 to be between them. Okay, that's way too much drawing on this picture. So let's go ahead and just go back to the original drawing that I had here. So now what you do is you start plugging in numbers. So I don't know, any number you want. Okay, let's go ahead and plug in 0. 0 is an easy thing to plug in. What do you get when you plug in 0? You get 0 times sine 0 plus 3 times 0. So you get 0. You might think we're done, but remember, I want 7 as an output, not 0. Okay, so 0 sounds good. We'll use that one. If you plug in 0, you get 0, so I'm getting a number less than 7. Now I need another input where I can get a number bigger than 7. Now, because it has sine there, and we're not going to be using a calculator, you want to plug in something that's easy to plug into sine, and maybe easy to calculate in general. So my advice is to plug in pi. Because if you plug in pi, look what happens. You get pi sine pi plus 3 times pi. Sine pi is 0, so you just get 3 pi. Do you agree that's bigger than 7? Yeah, it's 3 times 3.14, whatever. Definitely bigger than 7. This is less than 7. That's bigger than 7, so that's going to work. So my interval is going to be 0 to pi. Now, I'm not saying that's the only interval you can use, but as long as when you plug in one number, you get a number less than 7, and another number, you find another number that when you plug it in, you get bigger than 7, that interval will work. Of course, the function has to be continuous on that interval. We'll write all that down when we get to it. Okay, so now I want to show you that we can use the intermediate value theorem. So that means I have to show you 2 things are happening. And then if I can show you that, then we can use the conclusion of the intermediate value theorem and be done with this problem. Okay, so I'm going to write down. So now that we have our interval, what was it? We have 0 and pi, right? So we're going to write down the first thing. F is continuous on 0 to pi. Closed interval 0 to pi. Okay, why is this? So when you write that statement, you have to tell me why. This one's going to take a little bit more work than the last one, because the last one was just a polynomial. But this function's got a sign in it, so it's going to take a minute. Okay, it's going to take a few lines here, but it's stuff that we've gone over already. So here's the deal. So I'm going to start with the sign. So sine x is continuous on its domain because we had that result that said trig functions are continuous on their domain. So it's continuous. The domain is all real numbers. So it's continuous on negative infinity to infinity. So if it's continuous everywhere, it's definitely continuous on my interval because that's less numbers for it to be continuous at. Okay, so it's continuous on the interval, ran out of room, 0 to pi. That takes care of the sine x. Okay, now I'm going to try to build this function. So after the sine, now I'm going to just look at the x that's in front of it. Okay, x is continuous on its domain. Oh, maybe I should have wrote a little more here. So sine is continuous on its domain because it's a trig function. Yeah, write that down. Okay, I'm going to be looking for something like that. So because it's a trig function, x is continuous on its domain because it's a polynomial. So the domain is all real numbers. So it's continuous on negative infinity to infinity. So it's continuous on the smaller interval 0 to pi. So sine is continuous on 0 to pi, x is continuous on 0 to pi. So if you multiply continuous functions, you get a continuous function. That was another result we had. Oops. So I just showed you that if you do x times sine x, that's continuous on 0 to pi. I understand this is a lot of writing, but these kind of problems have a lot of writing. We're going to see problems down the road that are way more writing than this. So I want you to start getting used to it now. Okay, I'm still not done. I haven't built the function that I'm using. I built most of it though. We have x sine x. We don't have this 3x here. Okay, so let me go ahead and erase some stuff. I'm sorry that there's not enough room to write this whole problem down. So again, if I were you, I would pause it, write it down on a piece of paper, and then keep writing it so you can see all the stuff you need to write. Okay, so I'm going to erase everything except for the very last line there. Okay, so now we're going to talk about the 3x. Okay, so 3x is continuous on negative infinity to infinity. Well, let me first write on its domain. On its domain. That's because it's a polynomial. So it's continuous on negative infinity to infinity. So it's continuous on the smaller interval 0 to pi. Okay, and finally, since x sine x is continuous on 0 to pi, and 3x is continuous on 0 to pi, when you add them, you get something continuous on 0 to pi. When you add continuous functions, you get a continuous function. And that all means that x sine x plus 3x is continuous on 0 to pi. So yeah, that was a lot of words just to convince me that one's continuous because they threw the sign in there. Be careful, be able to do that. So once in a while I throw things like that on a quiz or an exam. It's a lot more difficult to write down than the last one where you just say, hey, it's a polynomial, it's continuous everywhere, so great. But it's not so bad if you think about it. You're just breaking it down into pieces using the results that we know. So if you look at the function that I started you out with, what is it made of? It's made of a couple of polynomials and of sine. So that's basically what you're doing. You're saying, okay, we know that's continuous, it's a trig function, so it's going to be continuous on our interval because it's continuous on its domain, which is all real numbers. This is a polynomial, so it's continuous everywhere, so definitely continuous on 0 to pi. So when you multiply them, you get something continuous on 0 to pi. This is a polynomial, it's continuous everywhere, so it's continuous on 0 to pi. When you add functions that are continuous on 0 to pi, you get something continuous on 0 to pi. So this entire function is continuous on 0 to pi. Truthfully, it's continuous everywhere, but all I need for the intermediate value theorem, the first thing I need is that it's continuous from 0 to pi. All right, so we finally did that one. So that one's done. Now we need one more thing before we can use the intermediate value theorem. Now that one's much easier than this step was here. So, okay, let me erase all this. Okay, so what was the second thing? What I need to do is I need to plug in 0 to the function, I need to plug in pi to the function, and I need what to be between them. The letter we used was n, but because I want 7 as an output, I need 7 between them. So the second sentence you're going to write is 7 is between f of 0 and f of pi. Again, if you would have minus the 7, you would have wrote 0 here instead of 7. But anyway, 7 is between f of 0 and f of pi, and let's go ahead and write that down. That's because f of 0, if you plug in 0, we already did it, but okay, I'll do it again. 0 sine 0 plus 3 times 0. You get 0, and that's less than 7. And we do f of pi, you get pi sine pi. Remember, sine pi is 0, so that term is 0, plus 3 pi. So you get 3 pi, which is greater than 7, right? It's 9 point something. So 7's between there. All right, so the two things we needed in order to use the intermediate value theorem, sorry, I want to use a green check. The two things we needed in order to use the intermediate value theorem have been satisfied. So we can use the conclusion of the intermediate value theorem. So I'm going to go ahead and have to erase some more. So since you're going to write the conclusion of the intermediate value theorem, you need to write down, so by the intermediate value theorem, there is a number. We're thinking of an input now. I basically want to say there's an input where the output is 7. But what's the number called? There's the number c. It's between what and what? Between 0 and pi. Okay, so I shouldn't write it that way. I'll just write between 0 and pi. I was going to put closed interval. That's definitely wrong. But again, you can write it's in 0 to pi. That's the same thing as saying between 0 and pi. Okay, such that if you plug in c to this function, you get 7. Okay, remember the whole time we want an output of 7. Now we're saying, yeah, there's a number c. The intermediate value theorem says there's a number c. So if you plug into the function, you get 7. That number c is between 0 and pi. And that's number c. If you were to plug it into here, you would get 7. That would make it a solution to the equation. So c is a solution to the equation. And that's basically it. Again, I know it sounds a little bit weird. It's really more understanding the theorem than anything else. Why the theorem is right is another story. It's a proof that we're not going to go over. But understand the statement so you know that there is a number c that does what you want. And I know it feels weird that we haven't actually come up with the number. We're not going to come up with the number. I have no idea what the number is. I just know it's somewhere between 0 and pi. That's the other thing I want to mention is that the problem says show it has a solution. Now I know not only does the equation have a solution, but I know that if you're trying to find it, you're going to plug numbers into the calculator and try to find it, you should guess numbers between 0 and pi because I know there's a number between 0 and pi that's a solution. Also, one more thing, I don't know how many solutions the equation has. Intermediate value theorem guarantees one for sure, but there might be more. So, for example, let's say you did this problem and later on you figured out the solution. Doesn't mean that's the only solution. There could be more. So it totally depends on this function. But if the function is continuous, it for sure has one solution, but it could have more. Okay, guys, that's pretty much the end of the story for this intermediate value theorem. Guys, please go over it and over it and over it again. Make sure you really understand it. And I definitely want comments on this one. Okay, I want to hear if you guys were able to understand the intermediate value theorem from this video. Okay, so please comment, let me know what's going on. Study hard, and I will see you next class.